Hello and welcome to the AI Research Roundup. I am Alex, your host. Today is May 8th, 2025. We are looking at a research paper, Low Precision Training of Large Language Models, Methods, Challenges, and Opportunities from Hugging Face's Trending List, published just 6 days ago on May 2nd. This paper surveys how training large language models can be more efficient using low precision training. This means using numerical formats, different ways numbers are stored, with less detail for key parts like weights, the model's learned knowledge, activations, its internal signals, and gradients which steer its learning. Alright, so building on that idea of different numerical formats, this first table gives us a great visual. It compares supported precisions across NVIDIA GPUs, from older architectures like Pascal to the new Blackwell. We see formats like FP32, a standard 32-bit floating point number, then FP16 and BF16, or BFloat16, which are 16-bit formats, and even FP8, an 8-bit format. The table shows how newer GPUs, especially their tensor cores, which are specialized for AI calculations, increasingly support these lower precision numbers compared to the general-purpose CUDA cores. This hardware evolution is key for making efficient training possible. Okay, so to help us understand all these different approaches to efficient training, this next figure provides a kind of roadmap of the survey. It shows how the discussion is organized, starting with basic knowledge, then diving into the main reviewed works. These works are grouped by the type of low-precision method used. For instance, fixed point and integer training, floating point training, and custom numerical formats. It also covers quantization-aware training, or QAT, which is a method where the AI model essentially practices using these less detailed numbers while it is still learning to make sure it performs well later. Then, the overview moves to system support and future research. Following that roadmap of different methods, this next bar chart gives us a historical perspective. It tracks the number of research papers reviewed from 2015 to 2024, broken down by the primary numerical format explored. We see bars for fixed point numbers, which are simpler representations, often with a set number of decimal places, integer numbers, which are just whole numbers, floating point numbers, which we have discussed, offering more range, and customized formats. It is pretty clear that research into integer and floating point methods has really accelerated, especially since around 2021, showing where the focus is shifting. Alright, to give us a clearer picture of what these fixed point, integer, and floating point numbers actually are, this diagram visualizes their structure. It shows how each format uses bits, the basic units of data. For fixed point types like Q7.8, bits are split for the sign, positive or negative, an integer part and a fractional part. Simple integers, like int16, just have sign and value. Then, floating point numbers like FP32 and FP16 use bits for the sign, an exponent, which handles the number's overall size or range, and a mantissa, which stores the actual significant digits. Understanding this bit allocation is key. So, after seeing how bits are laid out, this diagram shows a generalized model training pipeline, highlighting where low precision methods apply. We see forward propagation. That is the model making a prediction, where inputs, weights, and activations, those internal signals, are processed. Then, during learning, we have weight gradient and activation gradient calculations, which steer the updates. Finally, the optimizer state, which tracks learning progress, is updated. All these components, weights, activations, gradients, and optimizer states, are key targets for using those more efficient, less detailed numerical formats we have discussed. Building on that idea of targeting different components, this figure dives deeper into the fixed point and integer training methods we touched upon. It maps out the various studies, categorizing them. For instance, under integer training, we see general methods, then techniques specifically targeting optimizers, which, remember, track the learning progress, and methods focused on communication. It also highlights binary training. This is an extreme approach where values like weights or activations are reduced to just one bit, essentially on or off. This visualization really shows the extensive research in these specific low-precision areas, breaking down different strategies. So, as we have seen, the research into these low-precision approaches, using numbers with fewer bits, those basic units of data for key model parts, is really extensive, covering fixed-point, integer, and even binary methods. The work we have been discussing underscores how crucial these techniques are for making large language model training more efficient. It highlights diverse strategies, from quantization-aware training to compressing optimizer states. Though progress is significant, pushing to even lower precision, like 4-bit or 2-bit, remains a key challenge. That is all for this AI Research Roundup. I am Alex. Thanks for listening.